So I want to acknowledge the great team that's part of this. This wouldn't be possible without all these great scientists, and you've heard many of their talks here already. Certainly, Carrie Vahala talked earlier today, and the talk from EPFL also in the session before this. So we'll build very much on that core technology. So again, there's a bunch of talks in this session on DODOS, and this is the slide that kicked it off. It was the original kickoff meeting before the proposals were written, but it summarizes well what I think all of these talks will be about, which is generating combs of frequencies and generating a large enough comb that we can double F to 2F and mix those two terms together and then measure that offset frequency and stabilize that clock and beat down the noise and make a very, very stable optical source. So this is a NIST slide that summarizes this progression of optical clocks over the years from very large systems to tabletop systems, about 15 years ago, that again use fairly large high power lasers, fairly large mode-locked lasers. And the goal in this program that we're all trying to do is to reduce that size down and use different ways to generate these combs and do it with much lower powers and get away from these many watt systems. So this is the system that we're pursuing. So it's a tunable laser, a broadband tunable laser. I'll talk more about this technology. It's all integrated on a silicon substrate. And one key feature about our approach is that there are two resonators here. There's a terahertz resonator that provides the broad spectrum, 1F to 2F of frequency generation. And then there's this smaller FSR, 15 gigahertz one that we lock to one of these comb lines. And then we lock our tunable laser to one of the different of those comb lines separated by 15 gigahertz. And the reason this is a fairly low frequency is that we need to keep that difference within the range of what electronics can handle. So we don't want that to be hundreds of gigahertz, but we want it to be just something like 15 gigahertz. So these are the goals. It's a very aggressive goal in terms of stability, and you'll see where we are. So the different technologies I'll talk about will be the tunable laser technology, talk about the 15 gigahertz resonator technology, the terahertz resonator technology, some on SOAs, some on a 2-micron SOA, and then a Piplin doubler, and then that combines to go into a balanced receiver, and I'll talk about that as well. So the general approach we're using is putting everything on a single substrate. So it's all on silicon, and we're using indium phosphide materials for the 1550 nanometers, 1550 lasers and SOAs, as well as the 2-micron SOA. It's a strained indium gallium arsenide. We use silicon for all the waveguides and splitters, optical filters that go into it. We use lithium niobate bonded silicon for the doubler. We have done bonding of YIG for isolators. We're not intending to use that at this point, but that's in the background. And then silicon nitride is the fundamental resonator used for the terahertz comb. And then the final aspect is, again, 3D stacking of CMOS and photonics. So again, there's lots of components here, and the size constraint is rather severe. So this is the approach for the 1550 tunable laser. So it's a 3-5 material which is bonded to SOI. The waveguides in the SOI, there's current confinement in the 3-5 region, but that provides gain, provides lasing. That's what it actually looks like. That's the quantum wells. And in general, one bonds multiple materials at the same time. So when a company like Intel does this, or Orion, they're typically bonding something like 5,000 chips at a time. And any given PIC might have 4 or 5 different materials that are bonded at one time and then processed all together. And that's the general intent. Here's one example of that. This is just showing 3 different epis. So again, combining laser epi with modulator epi with detector epi. In this case, this structure is it's an array of 8 lasers and 8 modulators and 8 SOAs and 16 photodetectors. But at any rate, that's one of these patterns right here. So that's an example of that level of integration. This is the technology for the tunable laser. There's 2 coupled ring resonators. They have different diameters. So they have different free spectral ranges. They line up at one particular wavelength. And if you tune one slightly, then it hops over to the next mode. So this allows us to tune across a very wide wavelength range. The composite mirror reflectivity is shown here, and superimposed here is the gain bandwidth of the material. So typically only this one lasers. These are far enough out that they don't laze. And so this is the LI curve you get. These mode hops are when it's just what we're doing here is changing the current in the gain region, and we're not adjusting the phase adjustment here, and those are mode hops, those dips that occur. This is kind of an interesting laser because the Q in these resonators is fairly high, so the effective cavity length changes by factors of 3 or 4. When you're on resonance, it's a very long cavity length, much longer than the physical length here, and consequently the mode spacing is actually much smaller than you might expect. So this shows tuning across C-band at 1550 and line widths on the order of 160 kilohertz in this case. We have gotten line widths down to about 40 kilohertz, but this is pretty standard. So the second aspect now is to look at the technology for the terahertz and 15 gigahertz combs. So this is the silica work that Kari Vahala has developed, and the silicon nitride resonators developed by Tobias Kippenberg and Kartik Srinivasan at NIST. So again, we'll first talk about this technology, and then we'll talk about this technology. So the idea is to pump at a wavelength around 1550, and then generate these two dispersive waves that you heard described in the morning session, and do that with a reasonable power. So this is a simulation for a 75 milliwatt pump with a Q in this resonator of about 2.5 million. It takes very careful dispersion engineering, as described this morning, and very careful optimization of the coupling here so as to couple the pump in and get proper coupling of the 1 micron and 2 micron signals out of it. And lots of simulation to predict and the designs that one does going forward. So it's been a very elaborate effort from both Kartik's group and Tobias's group. Here's one example. So you can see one of these ring resonators with a pulley coupler around it. You can see here a range of structures with different free spectrum ranges, and then the two elements, the resonator with 2 output couplings, one for 1 micron and one for 2 micron. Again, the goal is that if we get this dispersive waves, the F and 2F, then we get much stronger powers than you get at other points, and the power coming out then gets above electronics threshold limit that we can use. So this is a calculation of the doubled 2F signal that gets here. Then the idea is we take the 15 gigahertz resonator and lock one of those combs to one of these lines across here. So this is, again, experimental. That was theoretical. This is experimental results. You can see the 2 dispersive waves, approximately F and 2F apart. This is work reported last fall at Frontiers in Optics by Srinivasan's group. And so that's what we're using. And so I'll go on and talk about the second harmonic generation approach that we're also integrating on the same nitride platform. So in this case, we're bonding lithium niobate to nitrides, and we're using this nitride as the waveguide to confine the light, and requires a very short coherence, very short Polding length here. This Polding length is only on the order of 5 microns on that order. One nice approach about what we're doing with X-cut Piplin is that it works directly with TE, and so you don't need a polarization rotator to make that work. And the advantage of the tight coupling is that efficiency is quite high, something like 2,000 watt per centimeter squared. 2,000 per watt per centimeter squared. So here's just some calculations of what the mode looks like at, in this case, I'll first show some results that we got at 1550 doubling. So the doubling signal at 775 and at 1550, and you can see they're both well confined in this structure. And that's the schematic diagram. This is what it actually looks like. And then this is a slightly different case. This is what we actually are doing, and which is bonding lithium niobate to silicon nitride resonators and putting the whole thing together. This initial structure I'll talk about is a silicon nitride waveguide on lithium niobate before it hasn't been bonded across. So this shows the doubling results. So we're getting efficiencies that are actually quite good, because the mode confinement is very high. And this just shows the second harmonic power being generated as a function of pump power and getting upwards of minus 10 dBm. So if you compare to other sorts of lithium niobate platforms, there are some advantages to this. basically the index contrast is quite high, so that means you get, again, good mode confinement. The film is quite small, so the effective area is only something like 2 microns squared rather than, say, 50 or 100 that you get with bulk lithium niobate. The losses are actually quite small as well, so it ends up working reasonably well. The second technology we're integrated on the silicon structure to enhance that is a 2 micron SOA. So in this case, we're bonding, again, epitaxial material. It's a different epitaxial structure than the 1550, but similar approach, PIN structures, and then the fabrication steps are the same. And this shows the gain that you can get. So this is, again, gain centered at 2 microns, gains of 13 dB. The next element on this is the 15 gigahertz comb that's been developed by Kerry Vahala's group, and he described that earlier today. So it's, again, there's lots of issues in terms of getting soliton, single soliton, low noise comb generation, and a lot of work to get these powers down to something that's very reasonable that we can supply with SOAs on 3.5 materials. So this shows one of the structures. He showed earlier today. The work that he's doing under Dodos is to include an integrated waveguide directional coupler with this rather than have a fiber coupler. And in the past, they've certainly seen very high Qs, and in this structure, they're getting lower Qs with the integrated directional coupler, but still very high, such that with just 22 milliwatts of power, they can generate 50 nanometers of comb spectrum. So very nice results. This shows the pulse width coming out of there, very stable soliton pulses, and this shows the resonators now integrated with that silicon nitride directional coupler, and that's been designed to match the waveguides that are in the 1550 chip on silicon. So one of the other technologies in here are balanced receivers. So again, there's multiple points where we need balanced receiver output, and in this case, it's a 1550 balanced receiver. And in this case, we need a balanced receiver at 1 micron, so both of those are under development. And this shows the technology that Andreas Belling's been developing at UVA. And again, it's a UTC design that they've used with NIST in other demonstrations in the past. And again, we need to get to at least 15 gigahertz in bandwidth, and they're getting 3 dB bandwidths of about 22 gigahertz with good responsivity. This shows one of the electronic chips that's being made, the TIAs, in this case 130 nanometer TIAs that made at Global Foundries that we're integrating with that balanced receiver. In terms of the 1550 approach, so Orion ultimately does the full system integration, and this is some of the technology they have. They have more efficient heaters than we have at UCSB, but this shows tuning across 45 nanometers, a very nice widely tunable laser, and a very nice tuning map. So again, as you adjust the tuning on those 2 ring resonator curves, it's very predictable. The nice thing is that they have very good efficiency. So again, the requirement here is very low powers, and they're getting efficiencies of 750 degrees per watt per millimeter, which is a very nice result. In terms of the tunable laser control, so this is a recent demonstration that was done at NIST. So it shows one of our tunable lasers packaged together and then controlled with one of the technologies that NIST has. That's what we're putting onto a CMOS chip. We don't have those chips yet, but we're using the technology they have there. And this shows again the package structure, and then basically the noise reduction you get by locking it to an optical wavelength. And so getting quite good noise in this case. So that's one of the key demonstrations to get us where we need to be for the total system. So to summarize, I think it is possible to demonstrate a widely tunable laser locked to a self-referenced octave spanning comb with reasonable powers. So powers of just 20 or 30 or 40 milliwatts for the very high frequency comb as well as the lower frequency comb. We've demonstrated lasers with about 40 nanometers tuning. The new chips that are in process should generate more. We generated, as you saw, silica waveguide whispering gallery mode resonators with 40 nanometers comb and fairly low powers, just 22 milliwatts pump. Terahertz combs with powers below 100 milliwatts, sometimes as low as 40 or 50 milliwatts. SOAs with gain, 10 dBs of gain, and Piplin doublers, again, with waveguide lithium niobate. Balanced receivers with sufficient bandwidth. This was a 1.5 micron demonstration. Andreas is working on the 1 micron version right now. And we've shown some initial examples of tunable lasers locked to one of these comb lines. So, thank you very much.